Swayam Prabha. Digital India. Educated India.
Welcome back friends to the week number 6 of our MOOCs course on the topic of principles of mechanical measurement, and this is the week where we are going to talk about the measurement of stress and strain. Now in the previous week we have discussed about the measurement of displacement or dimensional parameter, where you are introduced to quite a few different kinds of techniques for measurement of length scale. We have primarily restricted ourselves to measurement of smaller dimensions and mostly to electromechanical transducers, because that is the most common kind of transducers that you will find in any kind of mechanical measurements. That is some kind of mechanical input quantity being converted to an electrical output, and then that electrical output being calibrated back to that mechanical quantity. Now stress and strain, or particularly strain, is also something kind of a length related parameter, because it is just the change in length, or I should say the ratio of the change in length to the original length. And when I started our discussion on displacement measurement, I mentioned that whatever we are discussing there, they can be relevant to any parameters having a dimension of length, including the strains, or rather including strain. Now you definitely remember that we spent significant amount of time discussing about the resistive strain gauges, and that will be coming back again in this week, because that is the most common type of tool that we use for measurement of strain. But while we restricted ourselves mostly to the development of the mathematical expression for resistive strain gauges, and also discussed about different types of gauges, here we shall be discussing several other very important factors of the resistive strain gauges, and also hopefully we shall be able to discuss briefly about a few other kinds of strain gauges. So let us start our discussion. The first thing that we have to talk about is of course the stress strain relationship, where this curve I am sure all of you have must seen several times very early in your course. You know that within a particular limit, which we generally call the proportional limit or the elastic region, stress and strain are proportional to each other, represented almost by a straight line relationship, something like this kind of line, where the Hooke's law is applicable, that is stress and strain are proportional, and we get the simple relation, that is the stress is some constant multiplied by the strain, and this constant is known as what? This is the Young's modulus, all of you know, I am sure. And once we go beyond this elastic region, of course the stress strain relationship does not remain linear. It is a highly non-linear relationship depending upon which zone of strain that we are looking for. However, our discussion will be limited only within this elastic zone, or as long as this linear relationship is valid. Now if we talk about a very simple bar, say a bar of initial length L and initial diameter capital D, it has been subjected to some kind of force F. This is a subjective, it has been subjected to tensile force F from both direction, thereby causing some kind of strain to this. Because of this force, its length changes by this amount, like this particular amount change happens in one direction, similarly other direction, thereby causing a net change of length delta L. And so this is what we refer as the axial or longitudinal strength epsilon A, given by the ratio of the change in length, which is delta L, by the original length L. However, if the volume of the material has to be maintained, then this change in length must be accompanied by a corresponding change in the other dimension. So the diameter D, which was initially before putting the tensile strength, which is the initial diameter, that reduces to some value of D minus delta D, because on this side we have some amount of reduction, this side also we are having some other amount of reduction, or if I draw properly, say this is the reduction on this side. So this total leading to a delta D amount of change in dimension. and that gives you the lateral strain, that is the strain which is acting in a direction perpendicular to the direction of the force application. Epsilon L again it can be defined the same way, that is the change in length in that particular direction, that is delta d divided by the original length in that particular direction d, and the ratio of these two is given by the very famous number which is the Poisson's ratio, which is defined as minus of lateral strain to the axial or longitudinal strain, that is minus of delta d upon d by delta L upon L. This is the Poisson's ratio where the minus sign comes is because while generally if for the kind of situation that we are showing here, while delta L is positive, delta d is negative. So, to avoid a negative sign, the Poisson's ratio is given this minus symbol. Now, if we want to find the relation of these two strains, the longitudinal or axial strain and the lateral strain with the corresponding stresses, we can always, as long as we are within the elastic limit, we can always make use of the Hooke's relationship or Hooke's law. So, the stress in the axial direction epsilon A will be the Young's modulus times the corresponding strain. Similarly, the stress in the longitudinal direction will be the Young's modulus times the corresponding L. However, this particular situation is valid when we are dealing with only an uniaxial kind of load, that is the load is being applied only on one direction. If you are dealing with a compressive load, then what will happen? Compressive means when both this force F is acting in the inward direction in both cases. In that case, delta will be negative and delta d will be positive. So, the Poisson's ratio will always remain to be a positive quantity. However, the magnitude of the longitudinal and lateral strain, while their magnitude may change, their direction of course definitely will get reversed. And also, once we know one of the strain, we can always calculate the other one in terms of the Poisson's ratio. Like suppose we know here the epsilon A is given as delta L upon L. Now, how we can define the ratio delta D upon D? That can always be represented as minus of nu into epsilon A, which is our epsilon L. Therefore, using the idea of Poisson's ratio, just one of the strain is sufficient to represent the other one as well. Now, let us move to a more general situation where not one, but the force is applied in two different directions. So, for that purpose, let us initially consider a small rectangular block. Here we are restricting ourselves to 2 dimension initially. So, let us say this direction is x, this particular direction is y. Let me draw the rectangle properly. So, this is our initial rectangular block. This block is having a length of say L in this direction and or say L x in this direction and a length of L y in this direction. Now, we are subjecting this block to an axial strain or axial force acting in the x direction. So, let us say some force F x we are putting in this, then what is the corresponding stress that we are subjecting this to? F x will sigma x will be equal to F x divided by the area. So, the area over which it is acting, the cross section area is L y into 1, where 1 is the dimension in the third direction which we are not considering, that is F x divided by L y, or we can also write this one as F x by A x, where A x refers to the area perpendicular to the x direction. So, that is your stress that is acting in the x direction. Now, what will be the effect of this stress? This being a tensile stress, so there will be a increase in length in the x direction, and to compensate for that there has to be a decrease in the dimension in the y direction. So, because of this your system may take a shape somewhat like this. To clarify the image, I am erasing this force F x for now, just to make some. So, maybe something like this, let us say this is your F x. So, this is the increase in length in the x direction, whereas this represents the decrease in length in the y direction. Now, how much will be the increase in length? Let us say this is small a in x direction, this is small a in y direction, referring to the change in length because of the force acting in x direction. Now, how much will be your Ax? Ax definitely will be equal to, once we know the value of the stress, we can write this one as sigma x by E. This will be the strain that is acting in the x direction because of this force Fx. Similarly, how much will be Ay? Here we can make use of this Poisson's ratio to get the strain as again sigma x upon E, because Poisson's ratio represents the corresponding change in dimension. So, this is the deformation in the x and y direction because of this force Fx. Now, let me remove this Lx to make it get some more space. Now, we are putting another tensile force in the y direction, let us say its magnitude is Fy. Because of the presence of this Fy, there will be further change in the dimension of this body or in this rectangle in both directions. So, there will be elongation in the y direction, whereas there will be a reduction in length in the x direction. That means, if I remove the previous dotted line now, in the y direction initial length was somewhere here, now that will get elongated, and let us say this becomes the final dimension in the y direction. Correspondingly, this becomes the final dimension in the x direction, which was initially somewhere here. So, in the y direction, how much is the change in the length scale? The change in the length scale is this to this, where actual change or the final change is only this much, but this much change takes place because of the force in Fy direction. Let us say sigma y is the stress that is acting in the y direction, which is again Fy divided by Ay being the area which is having normal to the y direction, or we can write this one to be equal to Fy by Lx into 1 or Fy by Lx. So, let us say this particular thing is represented by By referring to the change in length because in the y direction because of the presence of this Fy. Similarly, this particular dimension is being referred as Bx, which refers to the change in length in the x direction corresponding to this force Fy. So, how much will be your By? By will be equal to, very straightforward, we know it can be written as sigma y upon E. Similarly, how much will be Bx? We can make use of the idea of the Poisson's ratio. So, it will be minus nu, that is Poisson's ratio, into sigma y by E. So, how much is the net change of dimension in the x direction then? There was initially an Ax increase because of the presence of force in the x direction or force Fx, plus there is a further Bx change because of the Fy. So, net change corresponding to Ax, our net change was sigma x upon E, and corresponding to Bx, net change is nu into sigma y upon E, that is 1 upon E into sigma x minus nu into sigma y. So, this is the net change in the x direction or net change in length in the x direction. Similarly, how much is the net change in length in the y direction? That can be Ay plus net By. So, your Ay was minus nu into sigma x upon E, that is the change because of the Fx, plus the change corresponding to Fy was sigma y upon E, that is this much into sigma y minus nu into sigma x. So, what is this then? This is the net change in length in the x direction, or this one can then be related to the sigma x, the net strain in the x direction because of both the forces. Similarly, this is sigma y, the net change in length or net strain I should say in the y direction because of both the forces. So, this way we can write then sigma x is equal to 1 upon E or epsilon x, I should write the strain in the x direction, net strain sigma x minus nu into sigma y. Similarly, epsilon y is equal to 1 upon E into sigma y minus nu into sigma x. If our interest is to know only the strain, then this is sufficient. However, if our interest is to know the stresses, then these are two equations which can be solved to get the two unknown sigma x and sigma y, and I am leaving the solution to you, but if you solve this, you will get that sigma x and sigma y will be coming something like E into epsilon x plus nu into epsilon y by 1 minus nu square, whereas epsilon y will be coming as E into epsilon y plus nu into epsilon x by 1 minus nu square. These two are the expressions for the corresponding stresses, and we can easily extend this one to 3 dimension analysis, where we shall also have this dimension z, the third direction. And by extending this, if we want to write a generalized expression, then your epsilon x will be equal to 1 upon E into sigma x minus nu into sigma y plus sigma z. Epsilon y will be equal to 1 by E into sigma y minus nu into sigma x plus sigma z. Similarly, the strain in the z direction, the new dimension that is being added, into sigma z minus nu into sigma x plus sigma y. So, this way we can generalize the Hooke's relationship to get a more generalized relation between the stress and strain in all possible direction. One important factor to consider here is the value of the Poisson's ratio. Poisson's ratio of course can have any value, typically most of the materials having a Poisson's ratio in the range of 0.3 to 0.4, but what can be the ideal value of Poisson's ratio if there is no change in the volume of the material? Let us say we are having a cylindrical element of diameter d and length L. So, how much is the volume of this? The volume of this material is pi by 4 d square L, and because of some kind of stress, suppose this L changes to L plus delta L and d changes to d plus delta d. Then the modified length is pi by 4 into d plus delta d whole square into L plus delta L. If we assume that there is no change in volume, this is the V prime, that is volume after modification. Okay, let us simplify this. Delta d and delta L both are being very small quantities, we can neglect any product involving them. So, it becomes d square plus 2 d delta d, delta d square can be neglected, into L plus delta L into pi by 4 into d square L plus 2 d L delta d plus d square delta L, the product of delta d delta L can be neglected. If there is no loss of material, then V will be equal to V prime. So, if we equate these two, then we have pi by 4 d square L on one side is equal to pi by 4 into d square L plus 2 d L delta d plus d square delta L. Let me erase this now, because this part is done, to make some more space for our writing. So, if we simplify this now, then we have minus 2 d L delta d is equal to d square delta L, and if we write this way, divide everything by d square L, then we have on this side and this side we have delta L upon L, that is minus delta d upon d divided by delta L upon L, which as per our definition is the Poisson's ratio is half or 0.5. This is the standard value of Poisson's ratio when there is no loss of volume, this or volume remains conserved, but practically their volume may not remain conserved even within the elastic limit, and Poisson's ratio typically takes a range value around 0.3 only, which we shall be using in subsequent discussions. Now, the principle of strain measurement. There are several ways we can measure strain. In early day instruments, generally they used to measure the displacement delta L over a certain length, and then the displacements used to be divided by the actual length, thereby getting the value of the strain. Extensometer is one of the earlier instruments where this displacement delta L used to be measured. Actually, modified form of this one is still in use in certain applications, but the idea in all such cases is to measure the displacement, then divide that by the initial length to get the strain. It was capable of measuring length changes over quite large scale. something like in the 50 mm to 25 centimeter like mentioned here. So, it is a quite decent range. However, the division was there, it was not sensing the strain, it was actually sensing the displacement. So, it actually falls in the domain of the displacement measurement like we have discussed in the previous week. But their modern instruments, they are actually directly sensitive to the strain. So, there is no need of just measuring the displacement and then divide that by a length to get the strain, rather we can directly get the value of the strain from the modern instruments. And this is how an extensometer used to be looking like, but there is no point discussing any more about this. The modern instruments for strain measurement can primarily be classified into three categories: resistive, inductive and capacitive. All these are so called electromechanical transducers. That is, the electrical quantity, or I should say the mechanical input, the strain is being converted to some kind of electrical output. In resistive instruments, the output change is caused by a change in resistance of the corresponding element. In inductive cases, it is caused by a change in inductance of the corresponding element, whereas in capacitive instruments, it is definitely a change in capacitance. Resistive elements are the most common one, the resistive strain gauges. They are mostly popular because they are generally available in very small size, so that they can directly be fixed on the specimen where we are looking for the measurement, and their mass is also negligible. Therefore, once we attach them to the actual specimen, it hardly causes any change in the characteristic of the system itself. However, inductive and capacitive ones are generally more rugged, and they are able to maintain their calibrated value over significantly long time period. So, there is no need to have repetitive calibration, and also resistive ones generally once they are attached to a particular instrument, we can't detach it and use it anymore. So, they are something like a permanent fixation to the specimen. That may not be always true for inductive and capacitive instruments, means they can be used for different kinds of systems. Inductive ones are generally preferred in permanent installations, and also they are very commonly used when our objective is not to measure the strain, but some other secondary parameter like pressure, temperature, etc. We shall be discussing in corresponding module. There are several strain gauge kind of instruments where actually we measure the strain and then we calibrate that to something like pressure or temperature. In those situations, the inductive instruments are preferred, whereas capacitive ones are more preferred in some special purpose applications. Their applications are much more limited compared to the resistive and inductive one. We can also have photoelectric or optical kind of instruments where again the final output comes in the form of some electrical quantities, but they are again generally special purpose uses. This is how a resistive strain gauge may look like. Some resistive element generally etched to a metal foil with a proper backing material, and they are resistive strain gauges are generally fixed with the specimen. So, once the specimen goes through some kind of deformation, they are able to directly sense that, and corresponding change in resistivity or resistance I should say is generally leads to a change in some kind of electrical quantity. The change in resistance can be sensed by a Wheatstone bridge kind of arrangement, or maybe some other arrangement, we shall be seeing one shortly. So, if we are looking for a Wheatstone bridge kind of arrangement, then this is the arrangement where one of the resistance actually can be the gauge itself. Under normal situation, this voltmeter senses 0 voltage, the null situation. However, whenever there is a change in the resistance of the strain gauge, there will be some voltage flowing through this, and that voltage will be a direct measure of the change in resistance, and which can directly be calibrated to the change in the strain, or I should say the strain. The mathematical part of this one was already done last week. We know that the gauge factor can be related to gauge factor defined as the per unit change in resistance to the corresponding strain can be expressed by relation like this, where the first part refers to the change in resistance corresponding to the change in length. This is the change in resistance, the Poisson's ratio appears there. So, this is the change in resistance corresponding to the change in the lateral dimension, and this is the change in resistance because of the change in resistivity. Rho is the resistivity here. So, we can rewrite this as a relation like this: epsilon is the strain, SH is the gauge factor which comes from the manufacturer commonly, and R is also the initial resistance of the resistor, which again is given by the manufacturer. Therefore, epsilon is a direct function of this delta R, that is any change in delta R can always be directly related to the strain. But strain gauges can sense only the resistance, or I should say the strain in one direction. Like here, this particular strain gauge will always sense the strain in this particular direction. tensile or compressive whatever, but direction remains unaltered. So, if we are looking for the measurement of multidimensional strain scenario, or if we are not sure about the direction from which the force is getting applied, we should have to go for such kind of strain gauge rosettes, where different gauges are placed in different directions. Like in this case, we can see 3 gauges placed over 180 degree apart in this scenario, whereas we can have much more complicated structure, something like this also, where each of the gauge will sense over a particular direction or over a range of directions, and then they can be combined suitably to get the final value of strain. In the next lecture, we shall be discussing much more about the strain gauge rosettes and how to do the corresponding calculations. These are some of the common grid materials that we use for making the resistance of the strain gauges. Their common values are given. Generally, different kinds of alloys are preferred: nichrome, constantan. These are very common alloys. You can see most of them are having a gauge factor of 2 something or in and around 2, but some of them are not. Where I am coming, their operating temperature is something very important, like the nichrome is able to operate to very high temperatures, and that is why they are generally preferred for high temperature use. When we are looking for a measurement something in the range of 700-800 degrees Celsius, nichrome is the preferred as a material, whereas materials like isoelastic or etc. are preferred generally at low temperature. There are a few other high temperature material as well, like platinum iridium can go up to very high temperature in the range of 1000 degrees Celsius. There are other materials like this constantan. Strain here, the value of Sg that is shown, that is generally the nominal value. It may change a bit depending upon the range of temperature. Why it can change with temperature? The logic is very simple. As the temperature changes, resistance can also change, and that can lead to a change in the corresponding gauge factor. The constantan is able to maintain a constant value of gauge factor over a sufficiently wide range of strain and wide range of temperature as well. Now, look at nickel. What it is giving is gauge factor is negative. It is a very high value 12, and also it is negative. That means the change in resistance is opposite to the direction compared to the others. It has also a very high temperature coefficient of resistance, and therefore, it has quite encouraging prospect. And even higher gauge factors, actually extremely high gauge factors we can find for semiconductor strain gauges. They have also very high temperature coefficient, and they are able to sense extremely small change in resistance as well, because the corresponding resistivity of the material is 10 to the power 9 micro ohm, or I should say ohm centimeter. Whereas for other common materials, something if you see nickel has only 7.8, whereas nichrome has 108 micro ohm, that is it is 108. If we compare their magnitudes, it is 108 into 10 to the power minus 9 ohm centimeter, whereas this is 10 to the power 9 into 10 to the power minus 9, that is 1 ohm centimeter. It is much higher, 10 to the power 7 times higher than nichrome. So, it can give you extremely high resolution, can sense very small changes in strain or very small amount of strain as well. However, they are not suitable for large strain measurement, because a large strain would lead to a very large change in the corresponding resistance, which is not preferred. So, semiconductor gauges are primarily reserved when we are looking for very precision measurement, or we are looking for measurement of extremely small values of strain. However, the materials like nichrome or platinum iridium or constantans are the ones that are very commonly used, depending on the corresponding temperature ranges. Now, you know that the strain gauges can be of several kinds, but the bonded metallic strain gauges are the most commonly used ones, and so we shall be discussing a bit more about them. The performance of bonded metallic strain gauges can depend on 5 different factors. The first factor is the grid material and configuration. Grid material, these are the desirable properties of the grid material, like we always want a high gauge factor, we want the resistivity to be high. For most of the common materials, the resistivity does not change that much with the strain, thereby the gauge factor Sg comes out to be 1 plus 2 nu, and as ideally nu is 0.5. So, this comes 1 plus 2 into 0.5 giving you 2. That is the most common reason for having the gauge factor to be around 2, but if the nu changes plus if we are having the resistivity change with strain, then its value can be something else, but that is something that happens to the semiconductor strain gauges in particular. But in general we want the resistivity to be high, we want high electrical stability and good mechanical properties, low hysteresis. Any kind of device we generally do not want hysteresis, because hysteresis will induce some error, but something of particular interest is low temperature sensitivity. We know that the resistance of resistor changes with temperature, and as if the resistance changes, then of course the calibration has to be done freshly, and the output also will be erroneous if we do not do corresponding correction or compensation. There are two ways the change in temperature can affect the performance. One, you know that the strain gauge materials, these are connected on some kind of backing. They are generally fixed by adhesive or some other kind of mechanism. Now, if the temperature increases, then the bonding between the wires and the corresponding backing material, that also keeps on changing, that becomes weaker, thereby producing an additional strain on the resistor element. Now, your sensor generally is not able to distinguish this thermal strain with the imposed strain, and thereby putting an additional factor in the final output. And the other way it can change is the change in the resistivity with the with temperature. So, these are the two ways the temperature sensitivity can affect the output, and that is why we always prefer the temperature sensitivity to be low, or we want the material, grid material, to retain its resistance over a wide range of temperature. The second factor is the backing material. The choice of backing material is important, particularly from mechanical stability point of view. These are some of the common backing materials that we can use. You can see their ranges. Epoxy is generally quite well preferred, because this is the normal range for several industrial applications. However, if we are looking to go for higher temperatures, then we have to keep on going in this direction, and ceramic based adhesives will be more preferable. Bonding materials and methods. Now, bonding materials definitely matters, means how you are connecting the grid material to the backing. There are several kinds of common bonding materials are available, and that is why several kinds, and generally all of them provide similar kind of performance. However, one parameter that is of utmost importance is the cleanliness of the measuring site. The measurement site has to be absolutely clean, perfectly free from any kind of dirt or oil or moisture, even paint also. That is, we always want the first the specimen to be cleaned to the as much clean we can have, thereby removing any kind of dirt and moisture from them, removing any traces of paint from that surface, and then fix the strain gauge on the bare surface with utmost cleanliness. Just related to that is the gauge protection. The gauge must also be protected from the surroundings. Surrounding can be coming from the dirt or dust particles flowing in. It can be related to the moisture, it can be related to some in particularly in when you are working in a workshop, it needs to be protected from some kind of mechanical impact. Generally the gauges, the manufacturers supply the gauges along with some kind of protective material in the form of some resins or maybe wax or some kind of epoxy kind of protective gears, so that the gauge can be protected from the surrounding. And the factor number 5, a very important one where we have to go for much more discussion, is the associated electrical circuitry. Now, we know that the change in resistance has to be measured by some kind of electrical circuitry, maybe a Wheatstone bridge kind of arrangement or some other kind of circuit, but actually the change in resistance is finally going to cause a change in some kind of output voltage or output current. Like in a bridge circuit, normally the output voltage is 0, and whenever the change in there is a change in resistance in any of the arms of the bridge, then there will be a change in the output voltage or some output voltage we are going to get. Now, you have to sense that output voltage using some kind of suitable voltage measuring instrument, and the depending upon the nature of instrument that you are using, the effectiveness of the strain gauge that keeps on changing quite a lot. So, we need to discuss a bit more about possible kinds of electrical circuits. The first kind of electrical circuit that we use in conjunction with strain gauge is something known as a ballast circuit. A ballast circuit is somewhat similar to a potentiometer application. Very simple, we have a voltage source something like this, we have a resistance connected with this, and this is your strain gauge. Let us say this voltage is Ex, R is the gauge resistance and Rb is this ballast resistor, and then across this you will be measuring this output voltage E naught. Mind you, here we are not at all talking about the loading effect which will be coming in by the when we mount some kind of voltage measuring instrument here. Here we want to check the sensitivity of the instrument or sensitivity of this particular circuit. Before that, let us write the general relations which we are going to use. As per the definition of the gauge factor, Sg is equal to delta R upon R by delta L upon L, the denominator being strain. We have epsilon is equal to delta R by R into Sg. Let us take some rough values. Let us say we are taking Sg equal to 2, which is the most common value of gauge factor, and R equal to 120 ohm. This is also quite a common value of this gauge resistance in several industrial applications. Now, look at this gauge circuit. Okay, before doing that, let us see how much will be the value of delta R then in this scenario. Your delta R is equal to R Sg epsilon, that is if we use these two values. So, we have 240 into epsilon. Now, suppose you are looking to measure a strain of 10 to the power minus 6, a strain value of 10 to the power minus 6, that is we are talking about delta L to be 10 to the power minus 6 times of the initial length. Then how much is the corresponding change in the resistor delta R, that is 240 into 10 to the power minus 6, that is 2.4 into 10 to the power minus 4. If we compare with the original value of the resistance, that is delta R upon R is 2.4 into 10 to the power minus 4 divided by 120. So, how much is it? It is, so we can write this one to be something like 2 into 10 to the power minus 6, or if we convert this to percentage, 0.0002%. That is, we are talking about an extremely small change in the value of this delta R when you are looking for measurement of strain like this. So, your circuit should be capable of sensing such small amount of strain or small amount of change in resistance, I should say. So, let us check the performance of the ballast circuit in this point of view. So, in this ballast circuit, say I is the current that is flowing through this. So, how much will be the current? I will be equal to the corresponding voltage divided by the net circuit resistance upon Rb. So, your E naught will be equal to I into R, that is Ex into R upon R plus Rb. So, this is the initial situation. Now, the because of some action of strain, this R changes to say R plus dr. So, how much it will be? If we differentiate this particular equation on both sides, then we have dE naught is equal to Ex is and Rb both are constant because they are unaffected by the strain. Only thing that is changing in this R by this amount dr. So, it will be equal to Ex into, we can perform the differentiation just the normal way, the denominator into differentiation of the numerator minus numerator into the differentiator form of the denominator, Rb being constant, we have Rb whole square. In the numerator R dr cancels out. So, we have Ex into Rb dr by R plus Rb whole square, or we can also write this one as Ex into Rb by R plus Rb whole square into dr upon R. So, this is the change in output, E naught initially having some value, this is the corresponding input dr, this is the, and your ballast circuit we have to check the sensitivity of this one. Now, how can we define sensitivity? Do you remember what was the definition of sensitivity? Sensitivity is the change in output corresponding to per unit change in input. What is your output here? E naught is the output. So, this is the change in output corresponding to the change in input dr. If we take the help from the previous expression, this one can be written as EEX RB by R plus RB whole square. Now, let us try to check what is the ideal value of this RB, the ballast resistance, so that we can get the maximum sensitivity of this instrument. How can we check that? That is possible if we differentiate this with respect to RB and set to 0. I repeat, we are trying to identify the value of RB or the relation of this RB with the initial gauge resistance R to get the maximum sensitivity of this instrument. So, we are differentiating the sensitivity with respect to RB and setting that to 0. So, what we are going to get? We are going to get EEX was there. So, we have R plus RB whole square TRB, oh sorry, we are just differentiating with respect to RB. So, minus RB into 2 into R plus RB divided by R plus RB whole to the power 4. So, if we simplify this, then we have R plus RB whole square minus 2 RB into R plus RB is equal to 0, or R plus RB minus 2 RB equal to 0. So, if we simplify this, what we have? RB equal to R. That is when RB and R, that is when the value of this ballast resistor is equal to the initial value of the gauge resistance, then the system will be having the maximum sensitivity. We can it can be proved, like if we get the second derivative and put R equal to RB, you can check what values you are getting. That can prove that this particular value corresponds to a maximum in the sensitivity. This I am leaving to you. You can check the second derivative and put R equal to RB there to confirm whether it is a maximum or minimum. This should give you a maxima in the sensitivity. Now, with this we are going back to our previous discussion. So, if we are having R equal to RB, then your d E naught is equal to EEX into RB becomes equal to R by R plus R whole square into dr, that is EEX by 4R dr, or something just like, or if we want to write in a different way, it can be written dE naught by EX is equal to 1 by 4 dr by R. So, this is the output of the instrument. So, corresponding any change in resistance dr, correspondingly you will be getting dE naught. If we want to compare this with the initial input that we have set in, that is this set of input we are talking about. We know the gauge factor we have set to be 2, R equal to 120 ohm, and now we know that ballast resistance also should be equal to 120 ohm to get the maximum output. Then how much will be your initial E naught? Your initial E naught should be equal to this much, that is EEX by 2. Let us fix up a value of say EEX is equal to 8 volt, which is a common battery voltage. So, this comes to be equal to 4 volt. Now, how much is then dE naught? Let us relate this dr to corresponding gauge factor, that is using this particular relation or the corresponding strain. So, it is 1 by 4 into dr by R will be equal to Sg into epsilon. So, corresponding d naught will be equal to 1/4 into Sg into EEX into epsilon. So, 1 by 4 into Sg is 2 into 8 epsilon, that is finally 4 epsilon. So, when your epsilon is equal to 10 to the power minus 6, your corresponding change in voltage we are talking about is just 4 into 10 to the power minus 6 volt. That is an extremely small change in voltage that we are talking about. Look at the initial voltage was 4 volt, and now we are talking about a change 4 into 10 to the power minus 6 volt. So, the E naught by E naught is equal just 10 to the power minus 6, which is an extremely small resolution that we are looking for from our voltage measuring instrument. So, despite putting the optimal condition like this, the ballast resistor circuit requires very high voltage measurement resolution to get a proper observation. That is the biggest problem with the ballast resistor circuit. While it is a very simple arrangement, quite similar to the potentiometer, but using this we generally demand a very high voltage requirement, and therefore is not always the preferred option in industrial application. However, if we are looking for some kind of dynamic arrangement, this can be preferred, because there we are not at all looking for the absolute change in strain, but we are trying to get a profile of the change in strain, and sometimes this one can give a good readings, but that is beyond the scope of present discussion. So, the second kind of circuit that we can have is the strain gauge bridge circuit. What we have a bridge circuit, a standard Wheatstone bridge kind of arrangement. I am sure all of you have some idea about the Wheatstone bridge, but still I am just drawing a simple Wheatstone bridge to refresh that knowledge. Let us say this is 1, this is 3, 2 and 4. These two ends will be connected to some kind of voltage source, let us say Ex. Let us give some names, say this is A, this particular point is B, this particular point is C, and this particular point is D. So, E naught is the output voltage. So, in a normal situation, or okay, if we write the equation, then E naught should be equal to Eb minus Ed. So, we can make use of the corresponding flow of current, like if I is the current that is flowing through this circuit, then I will get divided into two parts, one flowing through 1, another flowing through 3, and that way we can form the circuit, but we can always get the corresponding relation, so that Eb minus Ed can be represented as something like this. Eb should be equal to R2 divided by R1 plus R2, that is the voltage dividing relation. Similarly, Ed should be equal to R4 divided by R3 plus R4, or if we simplify this one, then what we are going to get, R1 plus R2, R3 plus R4. So, if we simplify this, then we have R2 R3 minus R1 R4, and if all these resistances are of equal value, then definitely we are going to, if all these R's are of equal value, that is R1, R2, R3, R4 all are equal to say some R, then what we are going to get from here, then you will get E0 equal to 0 under normal situation. Now, if one of these resistances are connected to a strain gauge, or rather instead of connecting one of the resistances, what we do, we connect two of them to two different strain gauges, but those two strain gauges are used in different ways. I am erasing this so that I can draw the situation. So, here situation is this 1 and 3 are kept vacant, 2 and 4 will be the normal bridge resistances. So, this is your 2, this is your 4, the normal bridge resistances, they will be connected to the output voltage measuring instrument, which is giving E naught, and you also have the supply voltage at these 2 points, which I am finding some difficulty to draw this, say okay. So, here you have this EEX. Now, what about 1? The 1 is connected to the strain gauge using which you are doing doing the measurement. This is your strain gauge mounted on the specimen where you are getting the measurement. And now, what about your 3, this particular one? This one will also be connected to another strain gauge, which will be not mounted on the strain gauge, this is more free, but that is kept, that is identical to the one, means they are the same strain gauge and they are located very close to each other as well. Only difference is that one is mounted on the instrument and this 3 is not at all mounted on the instrument, rather 3 is kept free, that is it is not at all not sensing any kind of strain. When one is undergoing some kind of strain, this 3 is not sensing any kind of strain. So, we have to now go for an analysis of this particular circuit. Let us just change our terminology a bit. Okay, there is no need, say 1 and 3. So, 2 and 4 are the normal bridge resistances, 3 is a strain gauge which is not at all sensing any kind of strain, but 1 is the actual strain gauge which is sensing the strain. Then 2, 3 and 4 their resistances will remain unaltered, but R1 will change by some delta R amount. So, corresponding change in voltage, say E naught plus D E naught will be equal to this R2 R3 remain unaltered, R1 will become R1 plus delta R into R4 divided by R1 plus delta R plus R2 into R3 plus R4. And if we put all the R1, R2, R3, R4 to be equal to R, like this relation, that is their initial values all are equal, then what we are going to get? Okay, we should simplify it a bit before going for that particular step. Is it at all required? No, maybe we can divide the entire both the numerator and denominator by R square. Then what we are having? We are having say 1 minus we are dividing by R square. So, we are having 1 plus delta R by R. Similarly, here we have R3 plus R4 giving us a value of 2 and another R goes here. So, you will be having 2 plus delta R by R EEX. So, you have a delta R upon R divided by 4 plus 2 into delta R by R, or you have to remember this initially this one was equal to 0. So, from there we get d E naught is or I should write d E naught by E x should be equal to delta R by R by 4 plus 2 into delta R by R. So, if we use the previous scenario, that is use the concept of the gauge factor, we take the same values S g equal to 2, R equal to 120 ohm, and as per our definition S g is equal to delta R by R by epsilon, giving us delta R by R is equal to epsilon into S g. So, if we put it back here, we have epsilon S g here divided by 4 plus 2 into epsilon S g here. Now, if we are looking for an extremely small resistance measurement like epsilon equal to 10 to the power minus 6, like in the previous scenario, then what we are going to get? In this case, this will be equal to 10 to the power minus 6 into 2 divided by 4 plus 2 into 2 into 10 to the power minus 6, that is 2 into 10 to the power minus 6 divided by 4 plus 4 into 10 to the power minus 6. So, which can approximately 0.5 into 10 to the power minus 6, because this particular part can be cancelled compared to 4, or we can write this to be as 5 into 10 to the power minus 7. So, again looking for an extremely small sensitivity, but the advantage here is that here the value of R is not coming into picture. That is, here we are not at all looking for we are not at all looking to measure this one with respect to the initial value of E naught. Initial value of E naught was 0. So, whenever there is a small change in R, let us, if we take say the same value E x equal to 8, then your d E naught will be equal to 8 into 5 into 10 to the power minus 7, that is what we have is 4 into 10 to the power minus 6 volt, that is 4 into epsilon, whatever magnitude of epsilon. So, the voltage that we are getting here, that is same, the change in output voltage is the same what we got in case of ballast resistor, but the advantage here is there the ballast resistor value we are trying to compare in terms of a potentiometer, where initially already 120 ohm was there, and with respect to 120 ohm we are trying to get a voltage value of this. But here we are not at all comparing this particular value with respect to this one, rather we are only sensing this amount of voltage. Sorry, I am making a mistake, it is not 120 ohm, 120 ohm was the initial value of I forgot the initial value, I think the initial value we calculated as something like 4 volt. So, with respect to 4 volt output voltage, initially we already have a 4 volt value at the output. Assuming a voltage measuring instrument which is having infinite resistance, you are already measuring a voltage of 4 volt, and in that 4 volt now you are trying to measure a change of 4 into 10 to the power minus 6 volt, which is extremely difficult. However, here initial value was 0, and there you are trying to measure a change like this, and that is possible to measure, that definitely can be measured. Therefore, very small, even very small change in resistance can be sensed by a bridge circuit like this, and once you are able to sense a small change in resistance, then you can definitely change that small amount of strain as well, which is of the order of 10 to the power minus 6 in this particular scenario. Now, the question is why we are putting this second one as well. You are having one resistance number 1 in the form of the strain gauge, that is fine, but why you are having this 3 as well? Because this 3 will be acting as some kind of temperature compensator. Like here whatever we are doing, that is corresponding to the reference temperature, at the temperature at which this gauge factor and others were calculated. But if there is a change in the surrounding condition, then the value of resistor R will change in 1. Similarly, the resistance in 3 will also change, because these two are identical, and so whenever their means their values will respond, or their resistance will respond identically to the change in temperature. That is why it is very important to keep this 3 to a location very close to 1, so that it is able to be able to sense the same environmental condition. And now, whenever there is a change in the resistance 1 because of the change in temperature, 3 will also suffer an equal change, and that will get reflected equally in this particular relation like this, thereby without altering your final output voltage and giving your final output as a temperature independent way. There are several others we can define the bridge circuit also, like the one that we have shown earlier, that is generally known as a quarter bridge arrangement, where you have the strain gauge mounted only on one of the bridge. But we can also have a half bridge arrangement, where on the specimen, on two sides of the specimen we are putting two strain gauges. Now, if this specimen is suffering some kind of bending kind of arrangement, let us say if this specimen bends like this, then what will happen? Strain gauge number 1 will sense a tensile load, whereas number 2 will sense a compressive load, and that will get reflected on this gauge circuit properly, and that will double your output voltage. Actually, this output voltage will get doubled. This is called the half bridge strain gauge circuit. If we want further sensitivity, we can even use a full bridge, where all 4 are mounted on the in the form of strain gauges, where both these two are like here all the gauges are stressed, but they are stressed in different way. Like you can see, this one and this one are sensing the compressive strains, whereas this one and this one are sensing the tensile stress. Means it is something like that. You have this specimen, this is a 3-dimensional the way I am trying to draw it. Now, two of the gauges are loaded here. Let us say, let us give some name to this, say 1, 2, 3 and 4. So, your 1 and 4 are mounted on the same side, and on the opposite side you have 2 and 4 mounted on the opposite faces. So, sorry, not 2 and 4, 2 and 3. So, 1 and 3, or rather 1 and 4 will sense the same kind of loading, whereas 2 and 3 will sense the same sense the opposite kind of stress. And now, when we connect them in a circuit shown here, then each of them will modify the voltage value in the same direction, thereby quadrupling, or I should say making the output voltage 4 times than what we should have got with a quarter bridge arrangement. We call this particular term a bridge constant. Bridge constant is defined as A upon B, where this A is the actual output that we are getting, and B is the output that we should have got if we are using just a single strain gauge in a quarter bridge kind of arrangement. So, when you are using a quarter bridge kind of arrangement, the bridge constant is 1. However, in this kind of situation your bridge constant is 2, because your output will be twice than what you have got with a quarter bridge. And what about in this scenario with full bridge? Here the output will be 4, or I should say the bridge constant will be 4. So, like in case of quarter bridge, if your output, like in the previous case we have got 4 into 10 to the power minus 6 volt, if you go for a full bridge arrangement it will be 4 times of this, that is 16 into 10 to the power minus 6 volt, thereby increasing the sensitivity of the output circuit. So, these two are the two most important kind of electrical circuitry that are used in conjunction with resistive strain gauges, the ballast resistor and this bridge circuit. We have a third one which is called the simple constant current strain gauge circuits, but today I do not have time. So, I am finishing the discussion here itself for the day. The simple constant strain gauge circuit we shall be discussing in the next discussion. So, the summary of the day, we have discussed about the stress strain relationship. Starting from there we discussed about the principle of strain measurement, and then we focused only on the resistive strain gauges. Then we discussed about different kind of relevant materials, the grid and backing materials. We discussed different factors which can affect the performance of bonded metal strain gauge, and then we have discussed the details of 2 electrical circuitry. I was supposed to discuss 3, but I think we should stop here because it is already late for the day. So, in the next lecture I shall first be discussing about the third kind of electrical circuit that we can use in resistive strain gauges. Then we shall be discussing about the temperature compensations, the way temperature compensation effect can be done. We have already seen that effect here, particularly in conjunction with the bridge circuits, but we shall be discussing a bit more on that. And then we shall be discussing about the strain gauge rosettes. There are several kinds of rosettes that we can have. We shall be discussing about a few sample rosettes. And finally, we shall be trying to see a few other ways of stress and strain measurement in mechanical systems. So, that is it for the day. I am signing off for the day. Thanks for your attention, and hopefully we shall be back very soon for the next lecture. Thank you.